Web development has a hoarding problem. You start with a fast, sleek application, but then reflexively pile on massive utility libraries for every minor feature. Soon, the whole structure grinds to a halt under its own weight. We have built up muscle memory to instantly run NPM install the moment we face a minor technical hurdle. But defaulting to these external packages for basic tasks actively degrades modern web performance standards. Google measures this degradation using a harsh standard called Interaction to Next Paint, or INP. It is the newest core web vital metric, and it is notoriously difficult to pass. This animated diagram breaks down exactly what INP looks for. It measures latency, that critical fraction of a second between a user clicking a button, the browser processing the action, and the screen updating visually. When an application appears fast but fails this test, the source of the failure often hides within the hidden structural dependencies, waiting for a user interaction to reveal a performance gap invisible during the initial load. The browser's JavaScript runtime is a single narrow pipeline. Rendering and background logic pass sequentially. Importing a massive utility library forces an oversized execution block into that pipe. Everything behind it halts. Layout changes and screen repaints are entirely blocked. To find out exactly how long these execution delays last, use high-precision tools. This documentation highlights performance.now, an API returning a millisecond-based timestamp with extreme accuracy to measure elapsed time during blockages. Optimization efforts that simplify the developer's workflow frequently translate into a direct execution tax for the end user. For years, JavaScript developers faced a frustrating technical hurdle, creating a complete, independent copy of a nested data structure. If you just copied the top level, the nested data remained tethered to the original. The most common legacy workaround was forcing the data through a JSON parse and stringify sequence. But as the split screen shows, that method is lossy. It strips away complex types, like date objects and maps entirely, causing silent data loss. To copy complex data safely without breaking their applications, developers standardized on importing heavy third-party library functions, like Lodash's Clone Deep. Today, the modern web has a native replacement for those heavy libraries. It is a built-in process known as the structuredClone algorithm, exposed to us as the structuredClone function. Look at this node tree duplicating itself. The native structuredClone algorithm traverses and safely copies complex types like sets, and it even preserves circular loops where an object references itself. It does this reliably with zero external code. Retaining legacy cloning libraries in a modern codebase simply forces the browser to download and execute redundant instructions. It drains main thread performance for a problem the platform has already solved. Time and date formatting has a similarly messy history. The original JavaScript date object is notoriously awkward to work with. Famously, the first month of the year is index 0, but the first day of the month is index 1. Those inherent language quirks drove the entire industry to adopt massive external time libraries, like Moment.js, to ensure they could parse and display dates accurately. But the browser platform has evolved. We now have a highly capable solution built directly into JavaScript, the Internationalization, or Intel, API. Here, you can see a stream of raw numbers passing through the native Intel.NumberFormat class. It effortlessly converts those raw integers into perfectly formatted global currencies, automatically applying the correct local decimal and thousand separators without needing a single byte of external logic. The Intel.DateTimeFormat class mirrors this exact efficiency. It allows you to display dates, times, and localized relative time strings effortlessly, adjusting for the user's local time zone and language settings out of the box. Bundling heavy localization libraries into your application is a costly practice that belongs in the past. The native capabilities are fully mature and ready to handle the workload. This is what the architectural aftermath looks like when you purge legacy utility dependencies from a codebase. As the total bundle weight drops, the application's execution speed hits maximum capacity. That weight reduction directly removes blockages from the single-threaded pipeline. By shipping less JavaScript to the client, you unblock the main execution thread and restore immediate responsiveness to every click and scroll. Consequently, that punishing interaction to next paint metric recovers. The latency gap closes, And the performance triumph is verified right where it matters most, at the user's fingertips. Senior engineering expertise relies on identifying the moment a third-party solution becomes a redundant layer over a mature native platform. Open up your own project's package manifest today. Look at the utilities you rely on out of pure muscle memory, and find the one you can ruthlessly delete.